We've been playing around with the weighted average in the last couple videos, learning about it, and it's time we do a problem. So here's the scenario. You're a medieval cook, and you're at battle right now with your army, and they just finished battle, and they're coming back to get some food. They're really hungry, and you need to start making some soup. So you have this soup pot with you, and it's represented by this curve here, y is equal to x squared, and what you take the area under that curve, rotate it around the y-axis, and boom, you got your soup pot. And just talking about units here on this soup pot, this top diameter here is going to be 2 meters, and then its height is 1 meter. Okay, and then talking about temperature, it's cold outside. It's 0 degrees Celsius, and you lit a fire and you're cooking this soup. And at the bottom, at the bottom of your soup pot, the soup is 100 degrees Celsius, and then at the top right now, it's 70 degrees Celsius. And in between, we have this temperature function, 100 minus 30y. And what I want you to do is find the average final temperature of this soup, and you're going to want to take a weighted average to do so. So given all of this, why don't you pause the video and try to work on this? All right. Assuming that you've given it a go, let's do this. So we want to find a weighted average. But maybe a good first question to ask is, why do we want to find a weighted average? Why can't we just take a regular average? Why can't we just take our maximum temperature, 100, plus our minimum temperature up there, 70, and divide it by 2, and we would get 85. Get 85 degrees Celsius. Why can't we do that? Why do we need to take a weighted average? Well, the main thing is looking at the shape of our soup pot here and looking at what our temperature function is saying. So our temperature function is saying you take a slice out, and you look at some soup at this y value here. You look at the soup across this y value here of this slice, and you're going to notice the temperature on this slice of all the soup on this slice is going to have the same temperature. That's what this temperature function is saying. Now, if you were to take a different slice, maybe towards the top of your soup pot, if you were to take a different slice up here, and again, look at all the soup in this slice, you would notice that all the soup in this slice also has the same temperature. Now, that's to say that the temperature up here, again, according to this temperature function, is different from all of the soup in this other slice down here. But all of the soup inside of one of these slices is going to have the same temperature. It's constant at a y value. That's what this is saying. Now notice, these two slices are different sizes. So that's really why we're taking a weighted average. If we were to just have a cylinder here and have the same temperature function and all of our slices would be the same, well then we could do a regular average like this. That would be totally fine. But that's not the case. We have these different slices going on at different temperature values, so we need to take a weighted average to compensate for those things. So given that, again, we need to figure out how to compute this weighted average. We need to find a few things. We need to establish what we have and figure out like what's weighting what. So let's talk about that. What I said over here is that we have a volume of soup. So we have a volume to work with, and we also have a temperature function. So those are the kind of two ingredients that we'll have in talking about a weighted average. And a good thing to do is to just ask ourselves, okay, before we start setting up all these integrals and evaluating them, why don't we just look at units first and make sure that when we set up these integrals, we're going to get the right units out. So let's check some units. Again, we said we have a temperature function and a volume to work with. So we have degrees Celsius to work with. And we also have this volume, which is going to be in meters cubed. Okay, and that is going to be what's multiplied in this numerator here and summed up. And what we now need to decide is, what do we need to divide by? What do we need to divide by in order to get what we want out, which is ultimately what? We want a temperature. We want an average final temperature out of this. So are we going to divide by meters cubed, or are we going to divide by degrees Celsius in order to get a temperature out? Well, we need to divide by a volume. We need to divide by meters cubed so that in the end, we get degrees out. We get a temperature. So we're just checking units to make sure that's the case. I'm not saying, don't mishear me. I'm not saying that we can cancel functions inside of integrals. I'm just saying let's check our units before we set up these integrals and make sure we're getting the right thing out. So now that we've established this, again, we said we want to compute a volume. So maybe we can look at how do we want to compute this volume and go from there. And we've already kind of shown how we want to do that. We have two methods to compute a volume that we know. We have the washer method and we have the disk method. So which would be the preferred method here? And I think the way that we've shown it shows we want to use the disk method. And again, that's because we have these temperature values that are going to be constant for a given Y value. So we're going to take a disk. Let's look at a disk here. Let's look at a disk that we get. And we've already learned about the disk method, so this should just be some review. And again, we're saying for a given Y value, we have this constant temperature across that Y value. So all the soup in here is going to be the same temperature. And setting up a disk, again, we want to end up finding a little dV, a little differential of volume. And with the disk method, that is going to be the area of this disk times a little differential. So this is going to be our radius. Our radius is going to be right here, and that's going to be x. And then setting this up, pi r squared, so pi x squared times this differential, which is going to be y. It's going to be a little dy, okay? And we have dy. And now, since we're integrating with respect to y, all we need to do is replace x squared with y. So that's dv is equal to pi y dy. And that's going to be all of our little disks summed up when we throw them in an integral. So given that, let's start to throw together our weighted average. Let's start to compute this weighted average. So we're going to have the definite integral, and maybe we'll save the limits of integration for a little bit. We'll throw those in at the end. So we're going to have a definite integral, and we said we're going to have our temperature function, 100 minus 30y, and we're going to be multiplying that by some little differential of volume. So we have pi y dy. All right, and then we're going to be dividing by the definite integral of pi y dy. And what are our limits of integration? Well, if we're integrating with respect to y, maybe scroll up just a little more. If we're integrating with respect to y, it's going to be from 0 to 1. So 0 to 1 on both of these. And now, I really want us to feel good about how we set these up. So let's talk about what they're saying. In this denominator here, this is just the volume. This is the volume of our soup in our soup pot, okay? And then in this numerator, again, this really goes back to what we were talking about earlier. This is saying for a given temperature value, we are weighting that temperature value with a volume of soup. All right, that's all this numerator is saying. So now we can compute these integrals and see what we get. So let's do that. So we're going to get, I'm actually going to pull pi out of this numerator and denominator, and then I'll distribute this y in this numerator. So we're going to have pi, I'm just going to leave it in white now, pi times the definite integral from 0 to 1. I pulled that pi out, and now I'm going to distribute y. So I have 100y minus 30y squared, and we're integrating with respect to y, and then we have divided by, pulled a pi out, let me grab some more space. Definite integral from 0 to 1, and then we have y dy. And now, anti-differentiating and evaluating, we get what? We get, these pi's are going to cancel, and then we have 50y squared minus 10y cubed in our numerator, and we're evaluating this at 0 and 1. And then in the denominator, we have y squared, grab some more space again, y squared over 2, and evaluating again at 0 and 1. So this comes out to what? We have 50 minus 10, and then we have 50 minus 10, and then when we evaluate at 0, this whole thing goes to 0. So we have 50 minus 10 in our numerator, and then in the denominator, we have, looks like 1/2. So this comes out to 40 divided by 1/2, which ends up being 80 degrees Celsius. That is our answer. So let's look at that. That's pretty cool. What is that saying? So we got 80 degrees Celsius as our weighted average. And if we were to compare that with the regular average that we took that was not weighted in the beginning, you can see that it's lower. And why is that? Well, like we were saying, we're taking each temperature value and weighting it with the amount of volume. amount of volume of soup at that temperature level. So as we look towards the top of our soup pot here, we have these larger discs going on. And at these colder temperatures, we have these larger discs. So that is why that's pulling our average down. And that's why it's less than our non-weighted average. These colder discs up here of soup are taking up more in our weighting, in our average here. So that's why it's lower. But hopefully that gave you some practice with trying to compute a weighted average. And we'll continue applying these in the next few videos.